Let's look at an application of exponential functions. The count in a bacteria culture was 800 bacteria after 10 minutes and 1700 after 30 minutes. So first, let's determine what was the initial size of the culture to the nearest whole bacteria. So when we're working with an exponential function, we're thinking about the form here, f of t equals a times b to the power of t. You can also set this up with f of t equals a times e to the power of kt. I think it's a little bit easier on these to just go ahead and use our base of b. So we can think of the given information as two ordered pairs. So our input is time, so our points would be 10, 800, and then 30, 1700. We can go ahead and plug both of these points into our function and then combine those equations. So we would have 800 equals a times b to the 10th, and 1700 equals a times b to the 30th. I'm going to go ahead and solve this first equation for a, so dividing both sides by b to the 10th, we have a equals 800 over b to the power of 10. We can then make a substitution and take this expression from equation number 1 and plug it into equation number 2 in place of a. So we have 1700 equals 800 over b to the 10th times b to the 30th. We can combine those factors of b together. When we're dividing, we subtract exponents. So this would become 800 times b to the 20th power from our 30 minus 10. We're solving for b, so go ahead and divide both sides by 800. And to find a value of just b, since it's b to the 20th power, we can take the 20th root on each side of our equation. If you put 1700 divided by 800 into your calculator, you'll find that that is equal to 2.125. So one way we could write our value of b as an exact value is writing the 20th root of 2.125. Another way to write this would be to have 2.125 to the 1/20th power. That would be another exact value for b. Or if we're using a decimal approximation, it's really important for ones like this where you're finding either a value of b or a value of k to keep as many decimal places as your calculator will show you in order to be accurate enough for our rounding in later parts of the problem. So this is equal to about 1.038407812. I'd encourage you to just use one of the exact forms of b and then just do your rounding on your final answers. So, looking at the first question here, what was the initial size of the culture? This value of a is what represents the initial size. Well, now that we know b, we can go back to one of our original equations that we wrote and plug in for b and then solve for a. So I'm going to use the one where I've got the green box there. So a is equal to 800 over b to the 10th power. So b, we said, was the 20th root of 2.125. Be sure to raise that to the 10th power. So as you're putting that into your calculator, be sure that you get your 20th root in there as well as your power of 10 in the denominator. So we need both of those in the denominator. It comes out to be about 548.795. A represents the initial size of our population, so we want to give that as a whole number of bacteria. So we're going to use our A equal to 549. So this is the initial size of our population, but we also, in calculating that, found an exact value for B. We'll continue to use that for later questions here as well. So let's look at another problem. Still the same function, the same setup. For our values of A and B that we found, what would be the doubling period for this particular bacteria population? So if we're starting with 549 bacteria, if that were to double, 2 times 549 is equal to 1098. So we want to know how long does it take to go from 549 bacteria to 1098 bacteria. So we're still thinking about our function in the form a times b to the power of t. So I'm going to plug in and solve for t. So we have 1098 equals 549 times our b. I'm going to go ahead and use my exact value of the 20th root of 2.125 to the power of t. Start by isolating, so I'm going to divide both sides by 549. So I have 2 is equal to the 20th root of 2.125 to the power of t. Since the thing we're solving for is in the exponent, this is where we need to bring in the inverse of an exponential, which is a log. So take some kind of log of each side of your equation. I'm going to go ahead and use natural log, but you could also use the common log. And that allows us to move this exponent of t out in front as a coefficient. So we've got the natural log of 2 is equal to t times the natural log of the 20th root of 2.125. So t is equal to the natural log of 2 divided by the natural log of the 20th root of 2.125. Put this into your calculator to find a value for t. We'll go ahead and round to just one decimal place. We get t is about 18.4, and our units of time here is in terms of minutes. So it takes this particular bacteria population 18.4 minutes to double. So that's to go from 549 to 1098 takes 18.4 minutes, and then to double again starting at 1098 will again take 18.4 minutes to get to just over 2,000 bacteria. Let's look at one other kind of type of question that we can see, finding the population after a given time or finding how long it takes for the population to reach a given number. So here for part C, this is when we want to think about doing an evaluate. So we're given an input at time, so we're going to be evaluating f of 120. To determine when a population will reach a given size, that's when we need to solve f of t equal to 14,000. So if you're given the time, we're going to evaluate. If you're given the population, then we're going to solve. So to evaluate, using the same a and b still here, after 120 minutes, we'll have 549 times the 20th root of 2.125 to the power of 120. This is finding a population, so we're going to give this again to the nearest whole number of bacteria. We get 50,551 bacteria. Solving is always the one that takes a little bit more work. To solve when our function is equal to 14,000, we'll have our 14,000 and set that equal to 549, our base of b, to the power of t, and we need to solve for t. Isolate first by dividing by 549. I'm just going to leave that as a fraction for now. We'll put all of that into our calculator here in just a moment. Since the thing we're solving for is in the exponent, we're going to need the inverse operation, which is to take the log of both sides. That allows us to move this exponent out in front as a coefficient. So our value of t is going to be the natural log of 14,000 over 549 divided by the natural log of the 20th root of 2.125. All of that needs to go into your calculator at once so that we're just doing one rounding at the end. So this should get us that t is about 85.9 if we do to one decimal place again. Since this is a time, our units here would be minutes. So given a time is when we want to evaluate our function. Given a population is then when we can solve. When we're solving an exponential equation is when we'll need to use our logs.